so that we can talk to each other and I can take you over some examples over how these things work. So all of this is something that is learned by breaking stuff and by experimenting, right? And by breaking stuff, I mean breaking down programs, right? So let's start with uh, the very, very basic, right? Let's start with something really basic. So tell me, how many of you have written code? I think everyone here has at least written a Hello World program, right? So, like, let's say within your ID, from the terminal, when you run that program, what exactly do you think happens? Like, how does the program run? Is anyone willing to answer that? Any guesses on what happens? How does code actually run on a computer? As computer science engineers, it's an important question to ask, right? So, once again, I ask you, whenever you write a program on a computer, even if it's just a Hello World program, how do you think it runs on the computer? What happens in between you typing a program that adds two numbers and it printing the output on the terminal? Anyone?
Can
Yeah,
you hear me?
yeah.
My basic understanding about this would be like a high-level complex language, which for which certain protocols have been written, gets broken down into simple logical circuits that are replicated on the computer, a circuit board, and then it finally gives us some output in a similar way.
Okay, so let me ask you. So the computer only has a set of very generic circuits, right? Like transistors and all. So how can a program be represented on, such simple electronics or such simple hardware? Like, do you think it just happens directly?
No, like through combination of multiple gates and then making them complex, like using universal gates, such in that
Okay,
way.
okay, that's like at a very low level. You reach that level like way towards the end, right? After you're done translating the program. So, okay, let me ask you a question. If I write a series of if-else statements, like if open bracket, do something, if close bracket, do something, if I type an if statement, do this, if I type a for statement, do this, if I type a while statement, do this, if I type printf, do this. I just encode a series of if else statements. Do you think I can create a programming language that way? Just by using if else statements and encoding the entire language. Like, your language has keywords, right? C has like 50 keywords. While, for, if, else, uh, then static, auto, main, all these are keywords, right? Or even a Python has some keywords where uh, like there's a print word, so there's a class, and there are functions. So if I just use a series of if-else statements, can we create a programming language from that? Why or why not?
I feel like that could be possible, but then the problem would be how would we represent the parameters that becomes complex? I mean, for this if-else conditions. But I feel like the entire programming language is built like if-else, if-else, if-else.
But for you can just write another series of if-else statements for parameters, right? That's not a problem. So I'll explain to you why this won't work. So let's say you have a series of if-else statements that represent valid code, right? So first of all, there is no way to check entire statements. Like let's say I write a sentence like if, for, else, while, and then open bracket, close bracket. So according to if else logic, that is a valid statement, right? For, if, else, while, open bracket, close bracket is a legit statement of code because you are not violating any coding principles as long as all those keywords are separated by one space and one open bracket and one close bracket. So you cannot represent a programming language using just if-else statements. It's not that simple. One is because programming languages allow you to define your own constructs, right? You can write recursive code, you can create structures, you can create your own data types. You can nest some code inside some other code. You can have loops inside loops. So what combination of those statements are valid and what are invalid? It's something that cannot be taken care of only by if-else statements, right? So let me start sharing my screen. Uh, screen one. Okay, let's share this. So I can you please join the stream? I hope that you all can see my screen. Can you see my screen?
So it's visible, it's clear.
Yeah. So let's write something very, very simple, like hello world. So let me just copy hello world from here because I'm very lazy and because I know all of you have used Geeks for Geeks at some point in the past, right? So this is a hello world program. So let this is a C program. Let's stick to C and let's stick to hello world. So this is an online tool known as Compiler Explorer. Okay, godbolt.org. So I'll be giving you all my examples on this so that you don't have to install anything on your machines to like write code. You don't have to install LLVM, you don't have to install GCC or any other compiler. You'll just be able to execute examples, including what I've given here. So the first thing my compiler has to do, right, is convert this into tokens. So let's choose a modern compiler where it's easy to see this kind of output. So I'll give it exclang from ASP. Let's see what it's converting. It's ASP dump. Good output. So, okay, dump. Next coming state. ASP dump. Dump. So dumping tokens is not something I do very often. So yeah, it's expand dump tokens. Okay, so they've changed the command. Never mind. Let's see if that works. No output file. Okay, but we have, yeah, great. So this actually worked. So let's scroll all the way to the bottom because over here you will notice something. So we have hash include stdio.h, right? So after that, what do we have? We have main, we have printf hello world. So what are we doing here? Look how the compiler is broken it down. So the first step is you have to identify each token. You have to identify that int is a word. Then you have to identify that main is a word. Then you have to identify a left open bracket, a right open bracket. Then you have to identify a curly bracket. Then you have to identify if the word printf, again a left open bracket, a double quotes, the word hello world, the string, then the closing parenthesis, a semicolon, return zero, and then yeah, this thing. So you can see here that the compiler, what it's doing basically, I'm using this command called exclang dump tokens to basically stop the compiler, right? So when the compiler does its job, it compiles it all the way through, like it will produce the output. but I don't want to produce the output. I want to run the compiler through a series of steps to show you how it works. So here you can see it has identified int, then it has identified an identifier called main. Then it's identified a left parenthesis, a right parenthesis, a left brace. Then it's identified the keyword printf. Then it's identified a string literal named hello world. Then it's identified a right parenthesis, so semicolon. So then it's identified the return statement, and then it's identified that you've given a numeric constant known as zero. Then it's identified a semicolon, then a right bracket, and finally the file is ended. So, did you understand what happened here? Basically, this program got converted to all these words. Now, my other question to you is, if I scrolled all the way to the bottom to see this hello world, what is all this stuff before that? This really long series of all of this code that the compiler is telling me that it's here. Where did all of this code come from?
Like header file.
Correct. It came from the header file. So I did hash include stdio.h. So since I'm doing exclang dump tokens, or in say GCC, in the GCC compiler, we have an equivalent word, right? A command called -e. So what this E does is it returns the preprocessed file. So now you can see that E has returned the code that the compiler actually runs, which includes everything inside stdio.h. So if you've ever wondered what is inside stdio.h, you can just give the -e flag, and everything included in hash include stdio.h will get expanded. So all of this code you see right from here till, like, going through all of this way till the very bottom where your actual hello world program is there. The actual hello world program starts at line number 495. So before that, it's just 494 lines of stdio.h. So that's what happened in the first step. You're breaking it down into all of this. So Clang supports GCC's options also. So I'll explain to you what is Clang and what is LLVM and what is GCC really soon. Don't worry about that. So this is the first step, printing individual tokens, combining all the code into one. So now let's go a step further. So let's go a step further. Let's see what happens after this. Great. That command worked. So the next flag is given. So flags are basically options you can give to your compiler. So this is something you might not have done if you have only done competitive coding, but it's a very common thing. Like let's say that you've written code according to a particular C standard, and you want to run the code according to only that standard. So there's a flag for that. Or like, let's say you want the compiler to give you some output, but not other output. You want it to filter the output. Or let's say you want the compiler to make your code faster, right? So then you can give flags like O0, O1, O2, O3, in increasing order of speed. So let's say you're okay with larger code, but you want the code to run really fast. So then you can give a flag like O3. So flags are basically options you're given to the compiler. So if you're ever like coding on your terminal, right? If you're not using Godbolt, then these options would be just given like, say clang, and then you give the flag like xclang and ast dump and then the file name dot c. So you just between you calling the compiler or you calling GCC and then -e and then file name dot c. So just between the file name and the name of the compiler, you include the options, right? So Uh, Let me make the font bigger for you so you can see this also. So yeah, just between the name of the compiler and the name of the file, you include options. So now let's see here, AST dump. So here what I'm doing is I told you, right, that if you just throw code, make code as a sequence of if else expressions, then you cannot represent what happens inside the code. As in, you can't represent that inside the main function there is a print statement, or inside an if statement there's a for loop, and inside that for loop there is another for loop. You can't represent that code like that. But there are data structures where you can represent, hierarchy. And one example of this is a tree, right? Like, let's say I want to say that, let me open up Paint. So let's say I want to explain that I'm adding two numbers, A and B. So like, let's say A plus B, and then I'm multiplying this whole thing by C, the multiplication asterisk symbol into C. So I'm doing A plus B into C. So one easy way of representing this, I just put A here, B here. Okay. Now let's just make two lines here to represent that this is A plus B. And then one other line, I say that this is the multiplication symbol and this is C. So, no, wait, let me just, okay, not C, the C is not just there. It's, yeah, here, yeah. So you're adding A plus B and you're multiplying that into C. So can anyone tell me what data structure this looks like if you've done DSA? Anyone?
Trees.
Trees. Exactly. It's a tree. So the compiler basically constructs a tree, right? A tree that has branches. So I think you can naturally see that this is a very easy way of representing code. You just add A plus B and multiply it into C. You can just look at that. So what here the compiler is doing is basically creating a tree. So you can see it is telling me that there is a compound statement. So what is a compound statement? It's just a statement with more than zero parameters. Inside that there is a expression. Inside that there is a cast expression. That means it's for the hello world that we're printing. There is a string literal inside. Innermost we have the string literal, so that string literal is hello world. And outside that, once outside of that, meaning like you have this printf statement right here, right? So in this printf statement is represented by this compound statement. You have hello world inside that, nested inside that. And outside that, you have a return statement. And finally, you have an integer literal, which is zero, which is the zero of the return zero. So I think you can sort of see how this looks like a tree. It has nesting. Even if it's not super obvious, maybe we can, like see some visualization, like let's say, yeah, there should be an option to see the this thing plan format. Okay, let's see if we can visualize this in some way. Okay, so I'll make it easier to visualize. Now I'll explain to you a problem, right? So let's say that I have 40, 50 programming languages. There are many programming languages there. Like there's C, C++, Python, Fortran, Ada, Lisp, uh, then I like Haskell, Prolog, whatever. I have all of these languages, and every language has to be converted to assembly at some point to run on the computer, right? So tell me, how can I avoid having to, like, let's say I have 50 languages and I have 50 different computers with different hardware. How can I avoid having to write 50 different implementations of the compiler on each system? Is there any way that you can think of that, like I have XYZ language and I want to run it on some different systems, but I don't want to write the language again and again. So how can I do that? Think about it. Any answers? Any guesses?
That's how the JVM works, right? It's the
Yeah,
right one.
yeah, that's how the JVM works. So the JVM is one example, but what does the JVM do? Java Virtual Machine, what does it do?
It converts it
It
to
read
bytecode first and then compiles the bytecode
Correct.
into.
So what is this bytecode? It's a common format, right? Like basically, what you're trying to do is I can convert all these 50 languages to one language and then just implement the backend for that language in each computer. That will work, right? Does that make sense to you? Like, let's say I have all of these programming languages, Java, Kotlin, C, C++, CMake, COBOL, whatever, blah, 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 blah. All of these languages. So I can write a programming language and then write a compiler to convert this programming language, my source language, to that language, and then just write uh, another compiler to convert that intermediate language to the language that the computer can run. So then I have to only implement the support for the intermediate language in all of the systems, right? Does that make sense? If somebody is not following me,
yes.
please, unmute and explain. That makes sense, right? So there is such an effort. Okay, this project to do this, it already exists, and it is known as LLVM. So you can see this image here, which I have for you. It is basically LLVM is something that used to stand for low level virtual machine. It no longer does. So the job of LLVM is to take all of these languages, C, C++, Go, Rust, or some other toy language, and convert it into a language known as LLVM IR. And then in your backend, you can support whatever platform. Whether you want to support Intel and AMD's platform, which is x86, or you want to support ARM, which runs on all of your mobile phones, or you can run RISC-V, which is a new upcoming platform, or MIPS or PowerPC, uh, whatever platform Mac OS X is running these days, right? So, what is this LLM project and why is it so important? So, this is something that was created by Vikram Adve and Chris Lattner in 2000 in UIUC. So it's a modular set of compiler and toolchain technologies that can be used to create the front end for any programming language and a back end for any instruction set architecture. So instruction set architecture is basically a word for uh, the instructions that your computer understands. So, like you might have Google Chrome on your mobile phone and you might have Google Chrome on your PC. But the Google Chrome running on your mobile phone is not the same as the Google Chrome running on your PC, right? Like, let's say that you edit, you write you have an executable on your PC. Let's say you have a copy of uh, GTA San Andreas or some really old game, an EXE game. You can't just copy that file to your phone and run it, right? Even though phones today are way more powerful than PCs from 10 years ago, so there is no lack of computational power here. Your phone can run PC games from 10 years ago, but it can't run that file, right? Is it just because your phone uses Android? No, it's not. Although that is one reason it's a different operating system. But even if you use Linux for desktop, some of you might have already started using Linux. The Linux that runs on a Raspberry Pi is different from the Linux that runs on your PC. because the Linux that runs on a Raspberry Pi is compiled for ARM and it has something known as ARM architecture. So for the phones, you might have heard of words like Snapdragon or Exynos or Adreno. So these are those CPUs made with a specific architecture, whereas PCs all run on x86 mostly, apart from Apple, which uses stuff like you might have Ryzen or Intel Core i3 or i5 or i7. So this LLVM project, it allows you to just write a front end for your programming language. And if you can lower your programming language to this thing known as LLVM IR, then you can instantly run your code on all platforms. Mostly. Like, it doesn't always work perfectly that way, but you can mostly do that. So it supports C, C++, Fortran, Rust, Objective-C, C++. So I want to give you an idea of how big this thing is. So if you are to compare web development to compiler development, right, then LLVM is equivalent to the entire MERN stack plus mean stack plus PHP stack plus Python stack. So this is an absolutely enormous project. You can see the GitHub project at LLVM/LLVM project, and you can see that the code has 417 branches. There are currently 21,542 bugs that are open, and it currently has probably something like 4 million lines of code. That's 40 lakh lines of code. And all of these folders that you see are different projects. Like Bolt is used to optimize binary projects. Clang is the front end of the C and C++ compiler. Compiler RT is the runtime that lets you run the code. Clang is a Fortran compiler. libc is the GNU C library implementation. Then you have LLD, which is your LLDB, which is your debugger. It's a debugger. You have LLVM itself. You have OpenMP, which is used to write parallel programs. So this thing, this project is not like one compiler. It's an entire tech stack. Okay, it's an entire tech stack in itself, and you can spend your entire life just learning. And if you wonder like who made it, well, all the companies, semiconductor companies that you know, like Intel, Nvidia, Qualcomm, AMD, ARM, and even some other non-compiler companies that work on compilers such as Apple, Meta, Google, Microsoft, Sony, all of them together have written code for this project. Okay. So it's built by all of these people together, and all of these people run it together. So you can imagine the scale of that thing, this thing. And the amazing thing is, because of the open source world, right? There is yet another compiler that is just as big as LLVM, which is built using an entirely different set of technologies and a completely different set of philosophies, which is known as GCC, which is the GNU Compiler Collection. So over here, instead of LLDB, you will see GDB, which is the GNU debugger. So all of these projects that exist for LLVM have a counterpart in GCC, uh, because LLVM was created after GCC. So many of these things in this compiler, both of the compilers, many of the options are built to work with each other. So that's the scale of this thing. So, like I've written like let's say all you've written a C compiler, it converts your C code to assembly, whatever, or however code is executed on a computer, and they run it, right? So if the compiler is already written, then what do you think people work on this today? Like, like have you ever wondered that, if Amazon's website already exists, then what do software developers at Amazon do, right? Obviously, the answer is that they develop new features and they uh, like you update the website and they keep it from breaking. But for compilers, I'm asking you, if there are already compilers that can compile the entire C language, C++ language, Python language, then why do so many people work on compilers and What do compiler engineers even do? Does anyone have any guesses? Any guesses? Any answers? Yeah.
Optimize the
Improve.
time frame.
Huh? Yeah. Please come again. I think two of you spoke at once. One person can.
Optimize the time constraint. I mean, like reduce it even by millisecond. The entire, I mean, even one process by millisecond, the entire, it might change the entire time limit. Time.
That's one. Okay. Any other answers?
Create more optimized code for the hardware.
Okay, so you're saying create more optimized code, but what does that actually mean? Like, let's say you might know about a little bit about time complexity, right? Like, if I use merge sort and I use bubble sort, merge sort is almost always gonna be faster than bubble sort, right? Because merge sort is like n log n time complexity, and bubble sort is like n square time complexity. Bubble sort just takes longer to run because it does more things. So when you mean optimizing code, what do you mean by that? Some code that is written is always faster than other code, right? Like there are always more efficient ways to write code. So what can the compiler do to help you out? Think any answers, any examples? Your answer
Type
is not
type
wrong. Just
inference.
think, huh?
Type inference should be one of them.
I mean, see, type inference is a solved problem, right? Like your compiler already does type inference. So what new type inference do you want to do? So you guys were on the right track. Let me bring you back on track. So just because a programmer has written code, is that code going to be the fastest possible code that can be written? Do you really think programmers are that smart that they always write the fastest possible version of a program?
No.
No, right? So let me give you a simple example. Do you know? So on a basic level, a processor can only add numbers or subtract numbers, correct? So if I want to do, let's say, 8 into 8, or wait, let's do 2 into 8. Okay. So how is my computer going to do this? It's going to do 2 plus 2 plus 2 plus 2 4 times. And yeah, I mean, it's going to just do that 4 times, 8 times, correct? Right? If I just do 2 into 8 and my computer only knows how to add, right? So it's going to do 2 plus 2 plus 2 plus 2 plus 2 plus 2 plus 2. So let's say that my processor takes, let's say you have a super slow processor that takes one cycle is equal to 1 second. So this is running 8 times, right? So how long is this 2 into 8 going to take to run? Tell me. If it takes 1 second
8
to run,
seconds.
8
8 seconds,
cycles.
correct? Exactly, 8 seconds. So now let me tell you a very cool thing about multiplication. Uh, can somebody tell me how 2 is written in binary? How the number 2 is written in binary?
1
1
0.
0,
0.
1, 0, correct. How is 4 written in binary?
1 0 0.
100.
How is 8 written in binary?
1 3 zeros. 1 and 3 0.
16 is written as 1 0 and 4 zeros. So what's the pattern here? Every time I'm multiplying by 2, what am I doing?
Increasing the number of zeros.
Increasing one zeros, right? So instead of like doing 2 multiplied into 8, right? Instead of doing 2 multiplied into 8, all I need to do is just write 2 in binary form, and like notice how many zeros. 2 power 1 has 1 0, correct? 2 power 2 has 2 zeros. 2 power 3 has 3 zeros, correct? So I'm multiplying by 2 into 8. So instead of doing this multiplication 8 times, what I can do the first time is I can just shift the 2 digits to the left and add 3 zeros, correct? What will that give me? 1 0, which was 2, and then 3 zeros after that, which is 16, correct? So I have to just, in one cycle, I have to calculate that how many zeros I need to put. And in the next cycle, I need to put those zeros. How long did that take? It took 2 cycles, right? 2 seconds, right?
Yeah.
So in just one operation, I've made code 400 times, 4 times faster, right? So
Yeah.
this is an example of an optimization. So what compilers can basically do is it can bend the rules. So if I write code, I want the compiler to run, give me the expected output. So when you have write code, that's the expectation that whatever you wrote code, you'll get the output for that. But you don't care that the compiler is running the code that you wrote. All you care is that the output should be the same. So as long as the compiler makes a change that is equivalent to your original code, you don't care, right? Like let's say you wrote a program to sort numbers, right? And you get a sorted list at the end. So do you care whether you it actually ran what you wrote, or whether the compiler did something in the middle that just resulted in a sorted list? So a lot of what the compiler does is making programmers life easier, right? So let me give you an example of this. So by the way, this 0 0 shifting which I showed you, it's a very famous optimization known as strength reduction. So in this, why is it called strength reduction? Because you're replacing a costlier operation known as multiplication by a cheaper operation which is known as bit shift. So in this example, you can go in reverse also, right? Let's say I had to do uh, 8 divided by 2. So if I had to do 8 divided by 2, my computer would execute it as 8 minus 2 minus 2, and then it would give me 4. So it would take 3 cycles. But you can shift bits the other way also, right? Provided that you know that a number is a positive number for some reasons. So if you know that you're starting out with the number 1000, and you know that you're dividing by 2, so 2 power 1. So you can just remove this 1 0 and you'll end up with 1 0 0, which is 4. So it works for division also. So this is an example of strength reduction, right? So there are more operations like this. So one I can show you is loop unrolling. Okay. So the example. So let's take an example at loop unrolling. So I hope that you guys are understanding why all of this is important. So I know this is hard to believe, but simple, small operations like this are the difference between your program taking hours to run and your program taking seconds to run. Okay, so it's that important. So loop unrolling, what it does is It's very simple. You have int x, you have a for loop, right? X is equal to 0, x less than 100, x plus plus, and then delete of x. Delete is some function that does something. Here we don't even care if delete is deleting. Now let's say that you know somehow that the code, or you know the compiler knows somehow that you are going to run the loop 5 times, right? So what happens here is, if you run the loop normally, then every time the compiler has to do a whole bunch of stuff. So let me show you a for loop. Like I'll show you one of my own programs only. So let me show you a code that I wrote. As an intern, I wrote a really shitty piece of code. So let, excuse the code, but I hope you'll understand. So let me show you this code. Let's go back to Compiler Explorer. So this is a very simple program. At least you guys write much better code than me, even as juniors. So you'll understand. But basically, all I have is a function known as quadrilateral, which accepts two inputs, int A and int B. And I have a main. So the main, in the main, I enter dimension A, dimension B, which is a length and breadth, and then I call the function. So if A is equal to 0, B is equal to 0, and A is equal to B, then uh, uh, it's a square with an area, this thing. Else, if they're not equal, it's a rectangle. Else, one of the values was 0, and then continue, and then inside quadrilateral line, just multiplying to find their area. Blah, blah, blah. Very simple, right? So now let's take a look at the this thing. What the new control flow graph. So there's this really neat thing where you can sort of visualize how code looks, okay? And this is really, really cool. So let me zoom out for you. So this is the assembly language representation of how the code loops around. So you can see that this is the body of my quadrilateral function, and it gets called from here again and again and again, and there's a loop here, right? And the code flows from one block to the other block, then it flows from this block to this block, and then finally it ends over here. You don't have to pay attention to the assembly. With enough time, we can learn that also, but today I'm just asking you to pay attention to the loops. So you can see that this arrow comes down here and it goes back up here. So basically, what I'm telling you is that whenever you run a loop, right, you have to run a whole lot of code again and again and again. But if you know that you're going to run the loop 5 times, so you can just expand that code and execute it 5 times. If your machine has like 8 cores, then you can just run one copy on each core and get the answer in one cycle, right? That makes sense, right? If you have 8 cores, then you can loop only on one core. But if you have 5 instructions in parallel or 8 instructions in parallel, then you can put all of the cores to use at once. So this is the magic of parallelization, right? So this is loop unrolling. So anyway, let's go back to our intermediate language, which I was talking about, that LLVM allows you to convert any language into any to run on any machine using a common backend. So this is done using something known as the LLVM IR. And again, it's hard to understand. So we'll have to start with a very simple program. So like the program to add to numbers VFD. So one good thing about compiler engineering is that you'll always work with very simple examples, because the moment you run a large program, right? Like let me show you this quadrilateral program again, and let me do S emit LLVM, and okay, I'll put O0 so that it's easier for you to understand. So Yeah, this is the output. And I don't think you'll have a very good time understanding what all of this is, right? It's very, very long, right? It's very long and there's a whole lot going on. So if you work on developing compilers, you'll be able to read all of this as easily as you're reading the left side. With some time, it will become more natural to you than English. So that's what you're signing up for. So let's start with a much smaller example, which is adding two numbers so that we never have to, go through all of that again because you're focusing on understanding how the internals work here. So I've given three options here, -O0, S, emit, LLVM. So here what I'm telling the compiler is emit the intermediate language. So if you take my image here, I'm showing you the output of the middle end optimizer known as LLVM, right? So I'm showing you the output of that. So let's go back here. So this main function, this green line here, corresponds to the green line here. So int main gets converted to define DSO local I32. I32 stands for int, and at main, then there's some debug code. Then there are various allocate statements, alloca I32, 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 which is basically allocating integers and aligning it 4 bytes at a time. Then you have your variables. So int a, b, and sum is equal to 0. So here you're calling various statements. And finally, there's a scanf. So in scanf, you are calling the scanf function. So it's calling ISO C99 scanf function, blah, blah, blah. And then after that, it's doing the actual addition here. So first, you might have studied in microprocessors and microcontrollers that data has to be loaded before it can be added, and then it has to be stored somewhere. So here the variables are represented by numbers. So %7 is one variable and %8 is one variable. So you load one integer, load another integer, then you add both of these integers in this instruction, and then finally you store the output in sum, right? And then finally you return this 0. So this is the output of LLVM IR. And finally, from this LLVM IR, you go to the end, which is the assembly. So this is the final assembly, which is the raw assembly where you see push instructions, move instructions. So you can see this int A, B. So uh, like I'll have to put an O0 flag to tell the compiler not to do anything smart so that it becomes easier to understand. But yeah, so yeah, now we have assembly. So here the scanf instruction corresponds to this thing. So you can, the good thing about Compiler Explorer is you can just hover over, some instruction and it will give a good explanation of what that instruction does. So move will move the data. Then you have add instruction which will add the data. So blah blah blah, and this is how it gets executed. So this is the final assembly. So there are a bunch of steps after this also. Actually, it's very complicated if you see the compilation pipeline, right? So let me show you. So it's the phases of a compiler. So basically, you have all of these steps. The first step that I told you, where we convert the thing into tokens, is known as lexical analysis, where you convert left bracket, right bracket, main. Then you have syntax analysis where you actually try to make sense of the code. Like if one left bracket is missing a right bracket, or if there is a printf statement with something illegal inside. Then you have semantic analysis where you do type checking, like are all of the data types correct? Am I trying to add somebody's name to a number? Or am I trying to add a float to an integer? What will I do there? Then you have your intermediate code generation, which is that LLVM IR and the AST we saw before that. Then you have code optimization. So optimizations are things that you do which I explained, like strength reduction, dead code elimination, copy propagation, loop invariant code motion. There's hundreds of optimizations out there, right? And then you finally do target code generation, which is generating our assembly code. Then you have to link it to the object files and finally generate your object file. And then finally it runs on your computer. You have to figure out how to load the data into your this thing, right? So I'll stop over here for the technical content, but I'll go a little bit over the job, what people do in this kind of things. So, basically, compiler engineers that work on compilers, they build the next version of programming languages. You code in C and C++ and Python, right? But somebody has to create Python and C and C++ themselves. Like they are just programs like other programs. So somebody has to program the programming language. So doing that is a job of compiler engineers. They implement optimizations. So changes that I make to computers, they make AMD processors all over the world go faster. And if Yashwant works on some NVIDIA GPU stuff, it makes NVIDIA GPUs all over the world go faster. You can make programs go from hours to minutes with the right sequence of optimizations and by making your compiler smarter. Like there are some optimization that might be obvious to you may not be obvious to the compiler. There's always room to make the compiler smarter. Nowadays, they're even trying to use AI to, make the compiler smarter. So we implement new features. So you might know that compared to whatever the C that we use in programming in C lab, which is your ANSI C, modern day C has a lot more features. Like if you see the C code that is written inside the Linux kernel, which is very recently it was C89. You could not put this curly bracket on on this different line from the main function. It had to be after the main function. If you put the curly bracket on the next line, it would throw an error. So, you know, programming languages get advanced. They have new features. Like now, if you see C++, it has an auto keyword. So you don't even have to declare data types. The compiler will figure out the data type and then it should be int, float, double, or what. You can just use auto everywhere and the compiler will figure out the most efficient data type for you. So we implement new features. We validate compilers. So think that, if you write a code and the code gives wrong output, so you blame yourself that I must have made a mistake in the code. But what if the compiler is wrong, right? The compiler might be adding 2 plus 2 to 5. But the thing is, the reason people trust compilers so much is that they're very rarely wrong. Unless you really, really push the compiler to the limit, it usually produces correct code, right? So we need to thoroughly test compilers that whether they're giving a lot of, you know, whether they're giving the right output or not. And this is a very difficult process that involves basically running the compiler against hundreds of workloads, using thousands of cores, and using several thousand gigabytes of RAM every day just to figure out if the compiler is right or not. And we also do a lot of research into new kinds of tools, techniques, processes. So like LLVM and Bolt. So Facebook has created a tool that can optimize binaries. So this is really crazy if you think about this. What it can do is even after you've written your program and compiled it into an executable, it can study the executable and make it go faster. And that's really crazy if you think about it because it's basically working at the assembly level and making your code go faster. So that's pretty mental and it's very hard to do. So compiler engineers come up with these kind of tools all the time. So it's a very well-paying field. And if you are the kind of person that likes C, C++ more than JavaScript and web dev, it's a very, very good and lucrative field to have a job in. Similarly, kernels and operating systems, which we'll probably uh, cover in the next session, is uh, is, is very similar because your operating system sits between your hardware and your. I'll stop sharing my screen. So your operating system sits between all of your hardware and all of your programs. So, like, there's a lot of clever things your operating system can also do to make things go faster. Although usually the operating system is much more restrained in that role, but your operating system has to make choices like what code to run. If I have 10 different processes that I'm needed to run, and I can run only one at one time, which one should I run? How should I allocate memory? Or, your RAM is much faster than the hard disk in your CPU or even SSDs. So even now that we have SSDs, the RAM is still about 10 times faster than the fastest SSD. And unlike SSDs, your RAM can be read and written to infinite times. So uh, your operating system has to know what to put in the RAM and what to put in the SSD. So there's an entire memory hierarchy, right? So kernel engineers work on the Linux kernel, they optimize it, and that's another entire field. So systems engineering can broadly be seen as everything that happens inside of the computer. If normal web development is everything that happens inside the browser, then systems engineering is everything that happens on the PC. So, contrary to what you might think, you don't really need a whole ton of hardware knowledge, but it's something that will come to you over time, right? So, I think that I've been talking for about 50 minutes. So, we'll end the session now. You all can ask questions, and if you don't have any questions, you can drop off. I'll put another poll if you guys are interested for part two. We can definitely have that part two. And other than that, you can ask me any question about compilers, about my job, about how much I make, anything like that. So feel free to ask questions. And if you don't have any questions, then it's already 12 in the night and you can drop off.
Yes, Priya, I had a doubt. Uh,
Yeah, yeah,
so in LLVM, there is an intermediate like LLVM IR.
yeah.
What does GCC do for making sure
Uh,
that it runs on every other architecture?
Yeah, so that's a good question. So one is that GCC is a more monolithic architecture than LLVM. So LLVM is built in parts from the outset. GCC was not built like that. But to answer your question, GCC's IR is called Jimple, and it has a second IR that's known as RTL. So Jimple is at higher level and it's closer to LLVM IR, whereas RTL is more lower level and it's closer to LLVM bitcode. So yes, the answer is that GCC does have an IR the way LLVM has an IR, but because of the way GCC is written, where the front end and back end of the compiler are more tightly coupled, GCC's IR is less useful than LLVM IR. So I hope that answers your question. So yeah, GCC is
Yes, Priya.
is called
What was that? GCC Jim call.
Gimple. Yeah, Gimple, Gimple. And the other IR is called RTL. It has two IRs. So soon you will
Why
learn
does it
that.
require two IRs?
So that's because you can design a compiler in very, very different ways, right? So now you see the new Fortran compiler inside LLVM. It uses a very different structure. It goes from source code to something known as MLIR, and then MLIR to LLVM IR, and then it goes to this thing. So basically, think that you have stages in the compiler, right? So, like, let's say that you saw LLVM IR just now. So, LLVM IR looks a lot like assembly, right? But what if you want to make some change in some? What if you want to do some optimization that is closer to the source code? So, like let's say you're doing some kind of machine learning, right? So machine learning has a lot of matrix multiplications. But by the time you reach LLVMIR, all of the matrix structure is gone. All you have is add and multiply and load and store statements. So if you want to do any optimization based on linear algebra, like there are optimizations based on linear algebra, like ways to compute sparse matrices and all, you can't do that on LLVMIR because all of that information is lost. The compiler has thrown away all of the context and it's converted something very, very simple. So if you want to do some optimization that's closer to source code, you'll need a second IR that is closer to source code. And if you want to do some other kind of optimization, then you might need something to maybe if you want to do some optimization that's dependent on target hardware, like some optimization that works only on AMD processors, then you might have to do it at a level below LLVMIR also. So it all depends on what you want your compiler to do. There can be any number of IRs. Some compiler might have no IR also. You might go directly from source code to assembly without any intermediate representation. So it all depends on what you want to do, whether you want performance, whether you want small code size, whether you want ability to do high level optimizations. So I hope that explains it.
Yes, Vaya, thank
Any other questions?
you. I had another doubt. Like, there are these different IRs or middle uh, layers that are there in between the source code and the object code, whatever we produce.
Yeah.
Wouldn't adding those layers cause any like unintended effect on the behavior of the code?
Meaning,
Like,
what can you? So I'll explain. So you have to understand there are two parts, right? You are asking me basically if I'm adding so many steps in between the source code and the final code, won't that also cause a slowdown in the program in a way, right? Is that what you're asking?
yeah, yeah, yeah,
Yeah, so you have to understand that there are two steps to any program, right? First, you compile the program and then you run the program. So when you compile the program, then you compile it only once. Like let's say when let's take GTA again, GTA San Andreas or GTA 5 or Microsoft Word or Windows. So when you get Windows, you only get an executable of Windows, correct? So who's the person who can compile Windows? It's some engineer sitting inside Microsoft. Only they have access to the source code. So the point I'm trying to make is code is run a lot more than it is compiled, right? You will run like any app like Swiggy or Zomato will be distributed to millions of people. Hundreds of millions of people, lakhs and crores of people will use the exe file or executable, but very few people who are working in Zomato or Swiggy will actually compile that code. So even if your compilation is a few seconds slower, if the final executable that your compiler produces, the final exe file or the final assembly, if that is faster, then isn't it a trade-off that's worth it?
yeah. So then, leading up to that question, like, would interpreted languages not benefit from this then? Like, since
Yes,
they are run line by line, you
yeah,
can't really optimize it through LLVM.
correct, correct. So that's why interpreted languages are always slower than compiled languages, right? No version of Python is as fast as C. So if you have an equivalent C program that is written properly, the C program, the executable of the C program will always run faster than the equivalent Python program. That's true. Interpreted
Yeah,
languages are always slower than compiled languages. So yes, but
okay, wait.
interpreted languages have their own advantages. Like one is that writing an interpreter is much easier than writing a compiler. And the second thing is that again, not all languages have the same role. In Python, if you see, Python is often used as a glue language. So if whenever Python is used to do machine learning, if you see the actual libraries like TensorFlow and all, they're often written in C++ or C, and Python is just used to call those libraries. So Python is just a wrapper for much faster stuff written in other languages. So you can get away with a very slow language as long as that language is calling code written in faster languages for all of the important stuff.
Got it.
Yeah. Anything else? Anyone else?
Baya, you were referring to the difference between executable and the compiled program. What
Yeah.
was the difference there? I mean, like, is the
Are you saying
compilation different and the executable different?
no? No, I meant that compilation is the process of generating the executable from the source code, and running the source code is just executing the source code on your PC, right? So if you are compiling some C program, you will compile it only once and you will run it many times. So like let's say you make a Sudoku solver to play with your friends or something. So you have to create the Sudoku solver executable. You have to compile the program just once, right? After that, you can just copy that exe file and send it to your friend. So that's what I meant.
But then doesn't that mean like optimization of the final executable folder is what like at the end gives us the
Correct. So
edge?
that is what the
Yeah.
compiler is doing, right? The
Okay,
compiler is
okay,
optimizing the executable. Now,
okay.
now I showed you that example with binary, like strength reduction, where it replaces multiplication with left shift. So whenever that code runs, whenever that executable runs, the processor needs to only shift left by 2 times rather than multiplying by 4. So which is much faster. So the executable is faster. So what I'm saying is a better compiler can produce faster code that will run faster on almost any machine. So yeah, that's the difference. Just like how some kinds of sorting algorithms are always faster than some other kinds of sorting algorithms, a proper optimizing compiler can make code that runs faster in general, like on any machine.
But yeah, sorry, another question that I had. So since since LLVM does optimizing and it can bend the rules a little bit of the source code,
Yeah.
can it also induce like vulnerabilities into the code itself because
Yes,
it's changing
that's
parts of
a
the
good
code?
question. So that's a good question, but this is typically not done by LLVM itself. It's done by combination of the compiler and the processor that's executing the code. So one example I can give you is your branch prediction, right? So what is branch prediction? Let's say I have if-else statements, correct? Like let's say that I write a program to execute the an if-else statement which is like 26 cases. It starts with the letter A and ends with the letter Z, correct? So I tell it that break out of the if-else statements as soon as the first letter of somebody's name matches the whatever input is the first letter of like say somebody inputs a name and Akash or something, and the first letter is A, then break out at A. If the first letter of that person's name is T, Tanmay, then break out at T. Okay. And I write this program. So I have 26 if else cases. And I want this program on an average to break out faster. So tell me, how can I make it go faster? Tell me, like, what comes to your mind?
Do the checking before you execute it first and then do the check or something like that. I believe like there was this vulnerability in branch prediction. Maybe it's
No,
that
no,
is not.
it's
I'm
a
not sure.
lot simpler than that. I'm starting with the letter A and ending with the letter Z, right? I'm checking through all of the alphabets, but human names don't start with the same letter number of letters, right? Like how many people in India will have a name starting with X? Like I don't know about you, but I have never met somebody whose name starts with X. Or maybe like I met one person whose name starts with X. Similarly, names starting with uh, Z or Y are also not very common. Names starting with A are very common. Names starting with like let's say uh, K, G, S, all of these letters are common. So if let's say I do a survey of like 10,000 names, and I see the frequency of names, and I arrange the if else cases in an order where certain letters are checked first, like A is checked first, then S is checked, then E is checked, and then finally the less common letters are checked. So on an average, I will have lesser comparisons before I break out, right? Because the common cases will be hit more quickly. Does that make sense to you?
Yes, Vaya.
Yeah.
So, but
So
then is there any way to find these vulnerabilities that may be found, or
so
maybe?
so I'm coming to branch prediction. So basically, what your CPU does is every time you have to compute a branch, every time a program has to take a branch, your CPU runs into a problem. It doesn't know what is the next instruction going to be. Normally, a CPU always knows what code it will execute next, right? After a print statement, there will be a scanf statement, then there will be a return statement, then there will be an end statement. But when you hit a branch, then your CPU doesn't know what to do. It has to compute the branch, correct? And while it is computing the result of that branch, it can't do anything else. So this will stall the CPU. So let's say I don't want to stall the CPU. So what can I do? Again, answer this question. Like, think about it. Every time I take a branch, the CPU has to stop to compute the result of that branch, and only then it can take that branch. While it's doing that, it can't do anything else. So if I want to reduce the loss of time that I have due to this, what will I do?
Execute whatever is there in that branch before checking it, or fetching whatever the value that you need to check
Correct,
it.
correct. So what I'll do is I'll execute the branch anyway, and then later I'll check if it was executed or not. If it was the correct, my prediction was correct, then I have no penalty. And let's say that 90% of the time I'm taking the branch. So you see most loops, right? Like for loops, like let's say a for loop is running 1,000 times, uh, and I'm doing I less than 1,000 and it's running. So it will run 999 times, and the 1,000th time it will break out. So for 999 times, the processor's prediction will be correct. Only once it will be wrong, right?
Yeah.
So this is basically branch prediction, or what you will call speculative execution. Okay, which is executing code that is not hit a condition here. So this is a security vulnerability that you can basically do nothing about, because for performance reasons we have decided that the trade-off of executing code sometime under the assumption that it is the right thing to do is a performance trade-off we've made. So there's an entire field of something known as secure compilation and execution. So in Linux, you have something known as SE Linux, okay, which forces user permissions, and it allows only certain programs to do certain things. And within compilers, there are compilers which guarantee correctness and safety over uh, performance. So like let's say you don't want very fast compilation, but you want your compiler to produce the correct output every time. So then there's something known as Misra checkers, MISRA, and there's an entire compiler known as Misra C. So that these compilers are compilers that will allow you to not do some things. Like for example, the NASA standard is there. It does not let you use uninitialized variables. If you are ever using a variable, you have to declare uh, variable's value to zero at least, and then it will not let you dynamically allocate arrays, because if you dynamically allocate an array, you might have a overflow. So you can put various policies into place, but then again, it's always a trade-off between performance and security. Like if you want your code to run very fast, then there are compilation modes like OFAST that will violate IEEE 754 standards. So it will do addition in illegal ways, and it will do rounding off and truncation in illegal ways to give you the fastest output possible. That output might not be entirely correct, but it will be very, very fast. So it all matters on what constraints you bring. So I hope that answered your question.
Yes, Bhaiya.
So you have to pick your constraints. Anything else? Okay, if there are no other questions, we can wind up for the night. I hope you all enjoyed this and learned something. If you have any comments on the session itself, I'd be happy to hear to them.
Thank you, Bhaiya. That's what I want to say.
Yeah, good, good.
I'm
So,
looking forward to the next part.
yeah, sure. Glad to hear them. Okay, okay, guys, you can drop off.